The Poisson distribution is a discrete probability distribution, and it applies to the number of occurrences of an event that happens over a specified interval. So in this case, we'll define the random variable to be the number of occurrences x in that interval, and therefore x can be just the counting numbers. It could be that that event never occurs in the interval, or it occurs once or twice, and in theory there is no upper limit. Now, what is the interval? Most of the time, it is time. However, we could look at it in terms of distance or area or volume. It just needs to be a specified interval. Most of the time we are looking at it, it will be time. The interval will be time. Okay, so we have some conditions for the Poisson distribution. The events have to occur with a known average rate over that interval if we're going to use the Poisson. The number of occurrences in one fixed interval must be independent of the number of occurrences in the other intervals. Okay, so independence is always important. What is the parameter of the Poisson distribution? Well, you'll see it written differently. Sometimes it's called lambda, this one, or sometimes it's called mu. Either way, however you write this parameter, it represents the population for the number of occurrences in the given interval. Remember, the mean is the expected number of occurrences in the interval. But how this will happen, what is the mean or the expected number? It is the number of events that have the highest probability in the distribution. So, the expected value of the distribution is the population mean. Sometimes this gets written as lambda, and sometimes it gets written as mu. It can be any positive value. It does not necessarily have to be a natural number, so it could be a decimal. Right? If you need to calculate this expected value, you can look at what's been observed, the number of events over the interval that it's been observed in, and then multiply by the desired interval length. We'll do an example of this. All right, so there's a couple ways we can notate this. I prefer the first notation, that x follows the Poisson with lambda. Sometimes they will just say p of mu. The standard deviation is always the square root of what is expected. Okay. The standard deviation is always the square root of the variance, and in this case the variance is equal to the expected value, so the standard deviation will be the square root of that. You'll see the formula written different ways depending on which parameter is used. So if we're saying that x follows the Poisson distribution and we use the parameter lambda, everything still stays the same. The mean is equal to the variance, which we will call lambda. In this case, the probability that x is equal to x, you take lambda and raise it to k. I'm sorry, this is the probability x equals k. So if x is equal to 2, then we take lambda, square that, and then e to the negative lambda, and then divide by 2 factorial. That's if you're calculating by hand. There is also this notation. If we say that x follows the Poisson of mu, where mu is the population mean, the mean is equal to the variance, which is equal to mu. Then instead of using lambda, you'll just use the mu's here. And sometimes they say k, as they did in the other example. Sometimes they use little x. Doesn't matter, that value comes up as the exponent and what you'll take the factorial of. Now those are probabilities for the Poisson calculating by hand with just x being equal to a specific value. We can use our calculators, right? Again, going to the second, we have to get to this distribution menu, so we'll go to second in the vars button. When you scroll down, you can calculate, the calculator will do it for you, the probability that x is equal to x. You have to put in that parameter lambda and the value x that you're looking for. And where our calculator is going to get really helpful is when we need to look at the cumulative values, where x is less than or equal to little x. And there, of course, we'll use the CDF whereas opposed to looking for a specific value, we use the PDF. Okay, so let's look at a specific example. So let's say a bank expects to receive 6 bad checks per day on average. Let's determine the parameter for this Poisson distribution. Okay, so the expected value is 6 bad checks per day. That is the mean, which also gets written as lambda, as 6. So we could say that x, our random variable, will follow a Poisson distribution with the parameter of 6. Now the variance of the distribution for the Poisson, sigma squared, is equal to the expected value, which you can write as mu, or as lambda, which is equal to 6. And then the standard deviation, sigma, is always equal to the square root of sigma squared, which is the square root of 6, which is approximately 2.45. So if we want to find the probability that x is equal to 10, we'll just use our calculators. We can put that in. It's the Poisson. Now this is just a strictly equal to, so we'll use the PDF. The Poisson has a parameter of 6, and we are looking our value of x to be 10. And when you put that into your calculator, it's approximately 0.0413. In this case, we're looking for the accumulation when the probability that x is less than or equal to 5, that they had received 5 or less bad checks in one day. So this time we'll use the cumulative, the Poisson CDF. The parameter is 6. The value of x we're looking for is 5. And when you put this into your calculator, you should get 0.4457. Okay, when you're using your calculators, remember that this needs to be an less than or equal to. So we have to rewrite this. The probability that x is less than 9, not including 9, since this is a discrete distribution, this is equal to the probability that x is in fact less than or equal to 8. And then we can put this into our calculators and use the cumulative function, the CDF. The parameter is 6. The value of x we're looking for is 8. And when you put this into your calculator, you should get 0.8472. If we start looking for values that are greater than, we'll use the complement. The complement of x being greater than 12 is 1 minus the probability that x is less than or equal to 12. So we can put this in. We can say this is 1 minus the Poisson distribution, cumulative, the CDF. The parameter is 6. The value of x we're looking for is 12. And when you put that into your calculator, you should get 0.0088. So there's about a 1% chance that the bank will receive more, 12 or more, more than 12 bad checks in one day.